Triply periodic bicontinuous materials, with their intricate microstructures and complex properties, have long fascinated researchers. This study delves into the microstructural and transport characteristics of 5 distinct models at a porosity of 1/2, seeking to establish explicit microstructure-dependent formulas for predicting their physical properties. The 5 models under investigation feature triply periodic bicontinuous porous materials with Schwarz P, Schwarz D, and Schoen G minimal surfaces, as well as 2 pore-channel structures. The authors meticulously characterize various microstructural attributes, including spectral densities, pore-size distribution functions, local volume fraction variances, and hyperuniformity order metrics. By leveraging this information, the researchers estimate effective steady-state and time-dependent transport properties using closed-form microstructure-property formulas. Notably, the time-dependent diffusion spreadability is exactly determined from the spectral density. The fluid permeability of these porous materials is accurately estimated from a closed-form formula dependent on the second moment of the pore size function and the formation factor, a measure of pore space tortuosity. The authors also establish rigorous upper bounds for permeability using the spectral density. A comparative analysis of the 5 models, each with identical cubic unit cells, reveals a striking correlation between permeability, inverse specific surface, hyperuniformity order metric, pore size second moment, and long-time spreadability behavior. These properties rank the structures in the same order, leading to conjectures about the optimal structures that maximize fluid permeability for arbitrary porosities. In the extreme porosity limits, the authors identify the corresponding optimal structures, providing valuable insights into the complex topological and structural properties of bicontinuous materials and their impact on physical properties. This research significantly advances our understanding of these materials, paving the way for further investigations into their properties and applications. Triply periodic minimal surfaces, a class of 2-phase media, have garnered significant interest due to their desirable physical properties and ease of fabrication using additive manufacturing. These surfaces, including the Schwarz primitive, Schwarz diamond, and Schoen gyroid surfaces, partition space into 2 disjoint but intertwining regions with identical phase volume fractions. They have been demonstrated to be optimal for various multifunctional performances, including heat transport, electrical transport, and bulk modulus. The macroscopically isotropic porous medium with the Schwarz P interface has been found to have the largest fluid permeability and mean survival time among a wide class of triply periodic porous media. This has led to the conjecture that the structure that minimizes the total interface area, proposed to be the Schwarz primitive minimal surface, maximizes the dimensionless isotropic fluid permeability. This paper aims to determine various microstructural characteristics, including spectral densities, pore size distribution functions, local volume fraction fluctuations, and hyperuniformity order metrics, and use this information to estimate effective steady-state and time-dependent transport properties via closed-form microstructure-property formulas. The paper focuses on the macroscopically isotropic fluid permeability, effective electrical conductivity, and time-dependent diffusion spreadability, with a particular emphasis on predicting fluid permeability theoretically for general microstructures. The authors generalize the conjecture for arbitrary porosities and show that it holds true in the extreme porosity limits by identifying the corresponding optimal structures. The paper provides background and definitions of microstructural descriptors and hyperuniformity, derives formulas relating transport properties to microstructure, and applies these formulas to compute the desired physical properties. The authors introduce 5 triply periodic bicontinuous models with porosity phi 1 equals 0.5, which are considered in this study. These models, illustrated in Figure 1, include the Schwarz P, Schwarz D, Schoen G, spherical pore, circular channel, and cubic pore, square channel models. The authors note that the 3 triply periodic minimal surfaces obey statistical phase inversion symmetry, meaning their domains of percolating phases are identical up to simple translation and reflection transformations. The paper is organized as follows. Formulas from Section 3 and results from Section 4 will be used to predict transport properties of the 5 triply periodic models. In Section 6, Conjecture 1 will be generalized to include structures that maximize permeability for all non-trivial porosities. Finally, in Section 7, the correlation between structural and physical properties of the 5 triply periodic media models will be discussed, along with open problems. The authors provide background information on microstructural descriptors and hyperuniformity, defining two-phase random media and introducing the phase indicator function I, x, omega, which specifies the statistical properties of each phase. The endpoint correlation functions S, I, n, x1, xn, are defined, giving the probability of finding the ends of the vectors x1, xn all in phase I. For statistically homogeneous media, the endpoint correlation function is translationally invariant, and the one-point correlation function is independent of position and equal to the volume fraction of phase I. The autocovariance function chi-v, r, is defined in terms of the mean zero fluctuating indicator function j, I, r, which is identical for each phase. The asymptotic behaviors of chi-v, r, are discussed, including its limit at r equals 0 and its behavior as r approaches infinity. For statistically homogeneous and isotropic media, chi-v, r, depends only on the magnitude of its argument r, and its slope at the origin is directly related to the specific surface S. In two-phase media, the spectral density, chi-v, k, is a non-negative function that can be experimentally obtained from scattering intensity measurements. It must obey a sum rule, where the integral of the spectral density over all wave vectors equals the product of the volume fractions of the two phases in the medium. For statistically isotropic media, the spectral density exhibits a power law decay in the Largic limit, with an exponent controlled by the specific surface area. In hyperuniform disordered two-phase media, the spectral density vanishes as the wave number approaches 0, indicating anomalous suppression of large-scale density fluctuations. This condition is equivalent to a sum rule in direct space, where the volume integral of the autocovariance function chi-v, r, over all space is exactly 0. Stealthy hyperuniform two-phase media are a subclass of hyperuniform systems, characterized by a spectral density that is 0 for a range of wave vectors around the origin. All models of triply periodic media investigated in this paper are stealthy hyperuniform. The volume fraction fluctuations within a spherical window of radius r are related to the spectral density through a Fourier representation, providing another way to analyze hyperuniformity in two-phase media. This representation enables the examination of hyperuniformity at varying length scales, allowing for a more comprehensive understanding of the complex behavior of two-phase media. The authors delve into the concept of hyperuniformity in point configurations, particularly in two-phase media. They introduce the power law form of the spectral density as k, right pointing arrow 0, leading to three distinct scaling regimes, classes, that describe the larger behavior of local volume fraction variance. These classes are determined by the exponent alpha, with class 1 being the most robust hyperuniformity class, encompassing periodic two-phase media and certain exotic disordered two-phase media. An explicit expression for the leading order asymptotic term in the asymptotic expansion of sigma squared v, r, for class 1 hyperuniformity is provided, involving a coefficient bv that depends on the characteristic microscopic length scale d of the medium. This coefficient serves as a hyperuniformity order metric, allowing for the ranking of different structures according to their ability to suppress large-scale local volume fraction fluctuations. The concept of pore-size functions is also introduced, including the probability f, delta, that a randomly placed sphere of radius delta lies entirely in the pore space V1. The complementary cumulative distribution function and the corresponding pore-size probability density function p, delta, are defined, along with the nth moment of the pore-size probability density. The importance of the mean pore-size delta and the second moment delta squared is highlighted, as they are related to diffusion properties and fluid permeability of the porous medium. The authors outline their approach to deriving microstructure-dependent formulas to predict transport properties, specifically the effective electrical conductivity sigma E of triply periodic bicontinuous media. Employing the strong contrast formalism, they derive an expression for sigma E, which involves a 3-point microstructural parameter zeta p that is a functional of the 3-point correlation function S, P, 3, R, S, associated with phase P. This formula has been shown to provide highly accurate approximations of sigma E for a wide range of phase conductivities and volume fractions. In ordered and disordered dispersions, theoretical predictions of effective conductivity and fluid permeability are explored. A novel formula for effective conductivity is derived, interpolating between two distinct dispersion topologies, providing a reliable approximation for bicontinuous media. The formation factor, quantifying the tortuosity of the entire pore space, is discussed in relation to fluid permeability. The complexity of theoretically predicting fluid permeability arises from its dependence on the dynamically connected part of the pore space. To address this, a cross-property relation is introduced, utilizing the second moment of the pore-size probability density function to approximate fluid permeability. This approach has been shown to be reasonably accurate for various media types. Rigorous bounds on fluid permeability are also presented, including the 2-point, void, upper bound, which relies on limited microstructural information. This bound is derived using variational approaches and has been generalized for 2-dimensional media and dimensions higher than 3. The evaluation of microstructural descriptors for triply periodic model microstructures is a pivotal aspect in understanding their spectral densities and structure factors. A key microstructural descriptor, the spectral density, can be derived by viewing each model as a certain packing of identical non-overlapping inclusions. This general packing spectral density formula is provided in equation 39, which depends on the number density of inclusions, their volume, and the structure factor of the centroids of these inclusions. The structure factor for any periodic packing of a single inclusion within a fundamental cell is given by equation 41, where the sum is over all reciprocal lattice vectors except for q equals 0. Substitution of this relation into the spectral density formula yields the corresponding spectral density for such a periodic packing, as shown in equation 42. Moreover, the importance of the diffusion spreadability, a dynamical probe that directly links certain time-dependent diffusive transport with the microstructure of heterogeneous media across length scales, cannot be overlooked. The time-dependent diffusion spreadability S, T, is exactly related to the microstructure via the autocovariance function chi v, r, in direct space or, equivalently, via the spectral density, chi v, k, in Fourier space, as expressed in equation 38. This relation allows for the evaluation of the long-time behavior of S, T, which is determined by the large-scale structural characteristics of the two-phase medium. Furthermore, the paper discusses the isotropic media, coated cylinders, model, which has been shown to be hyperuniform. This model realizes the upper bound of the 2-point void upper bound exactly, implying that it achieves the maximum permeability among all microstructures with the same porosity and pore length scale. The spreadability has been used to quantify a myriad of non-hyperuniform and hyperuniform heterogeneous media across length scales, with stealthy hyperuniform media characterized by the fastest decay rates of excess spreadability among all media with the same infinite time asymptotes. The authors present Table 1, displaying the values of the radial spectral densities, chi v, k, at the first 4 Bragg peaks, k equals qn for n equals 1, 2, 3, 4, for 5 triply periodic models with porosity phi 1 equals 0.5. These models include the Schwarz P, Schwarz D, Schoen G, circular channel, and square channel models. The results indicate that the Schwarz P surface has the maximum value of the spectral density at the first Bragg peak among all 5 models. The authors then derive the spectral density formula for periodic bicontinuous media, given by equation 43, which is equivalent to equation 46. This formula is used to evaluate the radial spectral density, chi v, k, which represents the angular average of the directional dependent spectral density, chi v, k. Figure 2 presents a semilog plot of the radial spectral densities, chi v, k, as functions of the dimensionless wave number kl, 2 pi, for the 5 triply periodic models with porosity phi 1 equals 0.5. The plot shows that chi v, k, is non-zero only at the Bragg peaks of the simple cubic lattice. Furthermore, the authors derive an explicit expression for the local volume fraction variance sigma 2 volts, R, for triply periodic media, given by equation 47. This expression is obtained by substituting equation 43 for the spectral density into equation 16. This work provides a comprehensive analysis of the spectral properties of triply periodic bicontinuous media, shedding light on their structural and optical properties. A study on the properties of 5 triply periodic bicontinuous models, with a focus on their volume fraction variance and pore size functions, has been conducted. The examined models comprise the Schwarz P, Schwarz D, Schoen G, circular channel, and square channel structures, all possessing a porosity of 0.5. Volume fraction variance, sigma squared v, r, has been calculated as a function of the dimensionless window radius r, L, with the results exhibiting a decay rate of r to the power of 4 for large radii, r, L1, across all models. Figure 3 displays a log-log plot of these findings, indicating that the Schwarz P and D structures have the largest and smallest variances, respectively. Additionally, a ranking of these models according to their large-scale volume fraction fluctuations is presented in Table 2, using the hyperuniformity order metric BV. This ranking, in ascending order, is as follows: Schwarz P, circular channel, square channel, spherical obstacle, Schoen G, and Schwarz D. Furthermore, efforts have been made to refine polynomial expressions for the pore size density function P, delta, in the 4 triply periodic models, utilizing the constraint at the origin P, 0, equals S, phi from direct numerical simulations. This led to an accurate fit for the square channel model, employing a cubic polynomial. Precise fits of P, x, with x is defined as delta, L, for all 5 triply periodic bicontinuous models have been established, represented in equations 49 through 53, and consisting of distinct polynomial expressions for each model. Equations 49 through 53 define the pore size density functions for each respective model, the Schwarz P, Schwarz D, Schoen G, circular channel, and square channel structures. Each model has its own polynomial expression describing its unique characteristics, such as the distribution of pore sizes. These mathematical representations provide valuable insights into the properties of these triply periodic bicontinuous models, which play a crucial role in understanding their behavior and applications in various fields. The pore size density and cumulative distribution functions of 5 triply periodic models with a porosity of 0.5 are analyzed, including the Schwarz P, Schwarz D, Schoen G, circular channel, and square channel structures. The dimensionless pore size probability density function LP, delta, and cumulative distribution function F, delta, are computed using polynomial fits and plotted as functions of dimensionless pore radius delta, L. The results reveal that the Schwarz P structure exhibits the largest support size, while the Schwarz D structure has the smallest support size. The mean pore size, second moment of the pore size distribution, and inverse of the dimensionless specific surface follow the same ranking order. Schwarz P, circular channel, square channel, Schoen G, and Schwarz D. The paper also addresses the estimation of transport properties, specifically diffusion spreadability, using the general expression for spreadability. By substituting the spectral density obtained from the angular average formula, an explicit formula for the diffusion spreadability is derived for the considered models. This formula enables the evaluation of spreadability over time. Notably, the first term in the sum dominates the expression due to the exponential decay of the spectral density with increasing wave number. This analysis provides valuable insights into the relationship between microstructure and transport properties in these periodic media. The excess spreadability, S, infinity, S, T, is plotted versus dimensionless time dt, L squared for 3 triply periodic minimal surfaces with porosity phi equals 1/2. Schwarz P, Schwarz D, and Schoen G. The circular and square channel models are not shown, as their curves are virtually identical to Schwarz P on the scale of the figure. The long-time asymptotic behavior of the excess spreadability is governed by equation 55, which exhibits an exponential decay with the same rate for all structures. The structure-dependent constant Cs, omega, is defined by equation 56, and is listed in Table 4 for the 5 triply periodic structures studied. The ranking of the excess spreadability at a specific time is consistent with the fluid permeabilities and other structural descriptors, as described in Section 7. The asymptotic formula, 55, is virtually identical to the exact relation, 54, for dt, L squared greater than 1, with relative errors within 10 to the power of 7%. The fluid permeabilities of the 5 triply periodic bicontinuous models are estimated using the approximation formula, 33, and the 2-point void upper bound, 35. The formation factor F is exactly given by equation 57 for the triply periodic minimal surfaces and is an excellent approximation for the 2 pore-channel models. The length scale LP involved in the 2-point void upper bound is expressed explicitly by equation 58, and the upper bound on the permeability is given by equation 59. The estimates of the dimensionless fluid permeability K, L squared from the 2 microstructure-dependent formulas are compared to direct simulations via the immersed boundary finite volume method in Table 5. The formula, 33, yields estimates within a factor of 2 of the simulation results, while the void upper bound provides the correct rankings of the structures according to their permeabilities. The dimensionless fluid permeability, K, L2, is estimated for 5 triply periodic models at a porosity of 1/2 using direct simulations, formula, 33, and the 2-point void bound, 59. The models are arranged in ascending order of K, L2, with Schwarz P exhibiting the highest value, followed by the circular channel model, square channel model, Schoen G, and Schwarz D with the lowest value. A generalized maxima permeability conjecture is proposed for all porosities, stating that among 3-dimensional porous media at any given porosity within a simple cubic fundamental cell, the dimensionless isotropic fluid permeability K, L2 is maximized for the medium in which the pore space is simply connected with an interface that minimizes the total interface area. In the low porosity limit, phi1 right pointing arrow 0, the circular channel model maximizes fluid permeability, with a pore space consisting of circular cylinders aligned along the principal axes and intersecting at the centroid of the cubic cell. The exact expression for the isotropic fluid permeability in this model is given by K approximately equals L2, 72 p 21, phi1 right pointing arrow 0. In the high porosity limit, phi1 right pointing arrow 1, the geometry that maximizes fluid permeability involves Stokes flow around a single solid body, which must be spherical to achieve an isotropic permeability. This spherical body is known to maximize fluid permeability in this limit. This study analyzes 5 triply periodic bicontinuous media models, including the Schwarz P, Schwarz D, and Schoen G minimal structures, as well as circular channel and square channel models. The researchers aim to determine various microstructural characteristics, such as spectral densities, pore-size distribution functions, local volume fraction variances, and hyperuniformity order metrics, for these models. To estimate the fluid permeability K for each model, an explicit microstructure-dependent formula is utilized, which involves the second moment of the pore-size function and the formation factor F. The results show that the estimated permeabilities are in relatively good agreement with direct computer simulations, with the Schwarz P structure exhibiting the highest permeability. This supports the conjecture that the Schwarz P structure maximizes fluid permeability in the limit of low porosity. The study also computes the time-dependent diffusion spreadability S(T) for all 5 models, which demonstrates the same trends as the permeability. A positive correlation is observed between the dimensionless permeability K, L2 and the inverse of the dimensionless specific surface, SL(1), the hyperuniformity order metric B, the dimensionless pore size second moment less than delta 2 greater than L2, and the long-time asymptotic coefficient C of excess spreadability S, infinity, S(T). The relative rankings of the 5 models according to these characteristics are consistent, with the Schwarz P structure possessing the largest values. The study's findings provide a comprehensive analysis of the microstructural characteristics and fluid permeability of these 5 triply periodic bicontinuous media models. The results support the hypothesis that the Schwarz P structure maximizes fluid permeability in the limit of low porosity, and the study's methodology can be applied to other bicontinuous media models to estimate their fluid permeability. This paper explores the structural and physical properties of 5 triply periodic bicontinuous media models, each with a porosity of 1/2 and subject to cubic symmetry. The authors present a comprehensive summary of key properties, including dimensionless specific surface, hyperuniformity order metric, dimensionless pore size second moment, dimensionless fluid permeability, and the long-time asymptotic coefficient of the excess spreadability. The study also delves into an analysis of phase inversion symmetry for the Schwarz P, Schwarz D, and Schoen G structures, demonstrating that these models possess this symmetry. This research aims to validate conjecture 2, which suggests that optimal structures with minimal dimensionless specific surface also maximize isotropic fluid permeability under given constraints. The paper concludes with a discussion on the need for future research to determine the triply periodic bicontinuous media within a cubic fundamental cell of side length L with minimal dimensionless specific surface for arbitrary porosities, subject to cubic symmetry. This research has implications for understanding the optimal design of materials and structures in various fields, such as materials science, engineering, and biophysics. Hyperuniform multifunctional composites, a novel class of materials, exhibit unique properties due to their specific structural organization. Building on previous studies on composite materials, this research explores their potential for optimizing multiple functions simultaneously, such as heat and electrical conductivity. The importance of microstructure in determining the overall properties of these materials is emphasized, with a focus on periodic and disordered hyperuniform systems in achieving optimal performance. Hyperuniformity, a specific type of disorder characterized by a uniform distribution of points in space, has been linked to enhanced performance in various applications, including photonic band gap materials, fluid flow, and radiation sources. Theoretical frameworks, including the concept of hyperuniformity, are explored to understand the behavior of these systems. In designing hyperuniform composites, the authors discuss the use of minimal surfaces and triply periodic minimal surfaces, which enable the creation of complex geometries with optimal properties. Statistical mechanics plays a crucial role in understanding the behavior of these systems, allowing for the prediction of their properties and optimization of their design. By combining these concepts, the study demonstrates the potential of hyperuniform multifunctional composites to achieve unprecedented performance in various applications, highlighting the importance of microstructure and theoretical frameworks in their design and optimization. The paper presents a comprehensive analysis of the relationship between fluid permeability and the structural properties of two-phase composite media, focusing on the role of hyperuniformity in enhancing fluid transport. Hyperuniformity, a state where the variance in the number of points in a given region decreases as the size of the region increases, has significant implications for material properties. A new methodology is introduced to simulate fluid permeability in two-phase composites using a combination of theoretical models and computational techniques. This approach utilizes the concept of diffusion spreadability, which measures the rate at which a diffusing particle explores the accessible space within a medium, as a probe to understand the microstructure of complex media across various length scales. The authors validate their approach by applying it to several different models of two-phase composites, including overlapping spheres and lattice-based models. They demonstrate that their method can accurately predict fluid permeability in these systems, highlighting the importance of hyperuniformity in enhancing fluid transport. The paper also discusses the connection between fluid permeability and other physical properties such as electrical conductivity and trapping constant, emphasizing the universality of the relationship between these quantities. A detailed comparison of their results with previous studies is provided, demonstrating the accuracy and versatility of their methodology. The paper concludes by discussing potential applications of this research, including the design of novel materials with optimized fluid transport properties. This work contributes to the development of new theoretical and computational tools for understanding and predicting the behavior of complex two-phase composites, with implications for a wide range of fields including materials science, chemical engineering, and geophysics.